Now let's look in detail at the case of single slit diffraction. As we just said, we can understand what's happening by drawing the wavefronts of the wavelets at different points on the slit, right? And we notice that those wavelets overlap on these regions. Now, what is this angle? That's an interesting question. How wide is that angle of the waves coming out on the other side, right? So what you can do is the following. You can start by dividing the slit into two groups. The top half and the bottom half of the slit, right? And then you look at some discrete waves, points or sources for the waves. This one for the top half, and this one for the bottom half. So if you do that, you will notice that your screen is going to be far away, right? So if it happened that at the point where you are, far away over there on the screen, if at that point the distance traveled by this wave and the distance traveled by this wave, this one is the first of the top half. This one is the first of the bottom half. So if this wave and that wave travel to get to the screen a distance that is a multiple of lambda, if there is an integer number of lambdas that you can fit here in this little section here, we already discussed that section, this distance will be lambda, in this case the distance of the slit divided by 2, that's A divided by 2, times the sine of the angle, that would be this distance. So if that distance, again actually if it's not a multiple, but say that it was half a wavelength, then this wave, when it arrives to the screen, would interfere destructively with this wave. And they will cancel each other over there on the screen, at that location on the screen. The important thing of this argument is that if that happens for this wave and this wave, it's going to happen for this one and this one, right? And if that's true, then it's going to happen for this one and this one. So basically, at that point on the screen, the waves coming from the single slit, they cancel each other in pairs. The wave coming from here cancels the wave coming from here. The wave coming from here cancels this one cancels that one. So everybody has a partner that cancels it completely. So at that point on the screen, you would have a dark spot. Now it's easy to predict where the dark spots are going to be, but not the bright spots. Because think about what's happening to the faces of this when you're looking at a point on the horizontal, which you might think it's probably going to be a maximum, right? Look at what happens. The face of this point and the face of that point are going to be the same, but those faces are going to be different from the face of this point and that point. So even the point that you think should be easy to figure out that it's a maximum, which is the point, midway over here, that point has contributions of waves with different faces. This one and that one have the same face, but this one does not have the same face as that one. So even if there is constructive interference pairwise, you don't know if there's going to be constructive interference globally. If all of those waves at some point are going to interfere constructively with each other or not. It's much easier these points where there is total destructive interference, but because there is no wave that survives, right? And which means that any wave that you consider should have another one that is canceling it out perfectly. So the condition that we're talking about is this one, that the difference in path length, which we have agreed that it was this little section over here, that the difference in path length between this wave and that wave should be, if it is half a wavelength, then those two waves are opposite in phase. So that means they're going to cancel each other. And the same will happen with the next two, second and the third one and the third one. So if this is true, you can be sure that there will be a dark spot on the screen. But of course, the same argument, so this tells you that at that angle, theta 1, you should find a dark spot on the screen. So that means that's going to be the boundary of this region. Right? This line should indicate the point on the screen where you're going to find the first dark line. And that will be given by this equation. But the argument applies just the same if you divide the slit into 4 pieces. Right? If you divide this into 4 pieces, then in the first top, in the top half of it, you can have two halves, and you can figure out that again, if the first wave of that top half of the half has this condition that a quarter of A, that a half of a wavelength fits in that distance, then that wave is, maybe I should draw it, this is not very clear. So the argument that we just made was, if I divide it in two and I make sure that this one cancels this one, right? The distance that we're using there is A divided by 2. And we said if that wave, when it arrives to the screen, and this wave, they're out of phase, so one is this way, the other one is that way, they're going to cancel each other, and this will be a dark fringe, right? But another possibility is that the waves cancel in pairs, but there is more pairs here. So that's what was in the plot that I just showed you. Now this is another possibility. Now I could make sure that this wave cancels this one, right? And that this one cancels this one. So wave number 1 is cancelled by 2, and 3 is cancelled by 4. To make sure that 1 and 2 are cancelled with each other, what I need to do is, well, I have exactly the same construction here, except that now I want this distance to be half a lambda, and I know that that distance is A divided by 4. Okay, so A divided by 4 times the sine of the next angle where I'm going to find a dark line should be equal to lambda divided by 2. And if it applies for dividing this slit into 4 sections, I can divide it into 6 sections, right? And then do the same thing. Little pieces in the first section, they cancel with the next one, and so on and so forth. So you can do it for any number of, even number of divisions of the slit. So the final result that you get is this one. It's an equation that looks exactly the same as the equation that you've seen before for the maxima of 2 slits, right? This is what we derive for the maximum of 2 slits. But the important thing is here is that this A does not refer to the distance between the slits, but the width of one slit. And second, very important, very easy to forget, is that this equation, when you're talking about diffraction, single slit diffraction, this equation tells you where the minima is, not where the maxima is. This equation tells you where the dark lines are going to be. It's not telling you where the bright ones are going to be. But if you know where the dark ones are, the bright ones are right in between them. So it's giving you pretty much the same information. But very clear that you make a big note and draw it and circle it many times, that this equation is telling you where the minima is. All right? So sometimes in physics, you've seen this, that we use the same letter for T for period and T for tension and so on, and that can be confusing. This is one, fortunately there are not many cases, but where the same exact equation applies to 2 different situations. And you have to know what you're dealing with to interpret the symbols accordingly and use it properly. So the pattern on the screen that you will see when the light just goes through one slit, not 2 but just 1, will be in the middle you would have a bright fringe. If light was little particles propagating, maybe the bright light, you would also have a bright light there, but it will be very narrow. But if light is a wave and the slit is very small, then the light is going to spread over a whole region like this. You're going to have a wide, bright middle central maximum. Okay, that is going to be white. And the location of the first dark line, it's given by y1 in the equation before. So you put sine of theta 1 equals 1 times lambda over d, and that tells you what theta 1 is. And if you know that theta 1, the angle at which you find the dark line, then you can figure out where on the screen that is. Right? So that will be your y1. And then if you want to find out where is the next dark line, then in the equation before, you plug in m equal 2, and that tells you the angle 2, and that translates into a distance on the screen of y2. So y1, y2, y3, and so on. So the intensity pattern that you see on the screen is something like this. In the middle, you have the brightest of all of the lines, so the intensity is a lot bigger. So this is intensity in this way, y location on the screen in that direction, and you have these minima occurring at these locations, here and here and here and here. And the amplitude of the maxima just keeps dropping. It keeps becoming smaller and smaller. So most of the times when you see waves going through a narrowing and they come out on the other side, most of the time, because this maxima is a lot brighter than these little ones, most of the time what you will see is this bright maxima, central maximum. That's what you saw in the picture, in the satellite picture. That region that looked like a cone with the waves there, that what you're looking at there is this region.